Stability of equilibrium. So in this actually we have discussed two methods, and the third one is very important method, and third one is the Z test method, right? So in case of Z test, so Z is nothing but height, nothing more than that. So this is just height. So as I said earlier, right? So if the potential energy is more, the body is tend to be unstable. If the potential energy is less, then the body is tend to be stable. Now if Z is more, then actually the body is going to be unstable condition. If Z is less, then actually the body is under the stable condition. So this is the only thing. So the summary of this. But so mathematically we will try to see that what happens. Suppose Z is a function of theta, some random function of theta. Why we call this as Z is a function of theta is, suppose there is a shape like this. On this particular shape, now this is x-axis and this is y-axis. Now the body is moved from this location to this location. Now actually I wanted to identify whether the body is under stable condition or not, or the equilibrium is stable or not. For that actually what I have to do is, so if I draw a line like this, so then actually it is making an angle of theta. And the height now, so this Z is a function of theta, right? So if you make a small angular change of theta, then Z is going to be stable or not, we are going to assess based on this particular function. Now here, how we are going to assess this is, so this is actually, this Z test is purely applicable for the, so when there is a force of gravity only, this Z test is very much useful for us. Now if Z is more, then the stability will be unstable. If the Z is less, then the stability will be stable, right? Now here, if Z is equal to f of theta, then dz by d theta, if I make it to 0, then we can find out whether the Z value is maximum or minimum. If Z is max, unstable. If Z is min, it is stable. Now how we can conclude this dz as theta is, so the body of this, the body is having a weight of W, let us say. I call this as mg, simple mg. Mg is the weight. Now mg into d theta equal to 0. dz. Mg into dz is equal to 0. Why? Because, so initially the body is under stable condition. If the body is under stable condition, then as per the principle of virtual work, right? So if you give a little displacement to that body, then automatically the work is going to be 0. So that is what is the principle of virtual work. Now mg into dz is equal to 0. If I divide with d theta, then it won't make any difference on either sides. That means dz by d theta I can simply take as 0. So why I am taking this as 0 is, this is a mandatory condition for the equilibrium of the body. So if the body is under equilibrium condition, then definitely at the equilibrium state, dz by d theta is going to be 0. If this is equal to 0, then the only possibility for Z is either it can be maximum or minimum with respect to theta, right? Now to identify whether the Z is maximum or minimum, we will take d square Z by d theta square, and if d square Z by d theta square is positive, d square Z by d theta square may be negative. So this is, in this particular case, whether we will have the Z value as maximum or minimum. In this case, the second derivative is going to be positive. If the second derivative is positive, then the possible value is only Z min. And here, if it is negative, Z is max. Now actually, suppose if the body is at this location, it is stable. And then I wanted to identify whether it is, stability is, sorry, the body is under equilibrium condition at this particular stage, and I wanted to identify whether this equilibrium is stable or not. For that, what I will do, I will give a simple virtual displacement and try to assess this value dz by d theta and d square z by d theta square, and finally I will depend on this d square z by d theta square whether it is coming out to be minimum, positive or negative. If it is positive, then actually I can conclude that the stability is, the equilibrium is stable. Otherwise I can conclude that so the equilibrium is unstable. Got it? Understood or not this concept? Is this understood? So no complexity in it. So Z test is actually, we are applying this Z test for finding out the equilibrium, whether it is stable or not, in case of whether the gravity is the only force. So in such cases, we are identifying, depending upon the principle of virtual work, we have got the condition that dz by d theta is equal to 0, provided z is a function of theta, which you have expressed intentionally like this. And if this is equal to 0, and based on the second derivative, if it is coming out to be positive for a certain value of theta, when theta equal to alpha, if this value is d square z by d theta square is equal to positive value, then we can conclude that the equilibrium is stable. If it is negative, then we can conclude that the equilibrium is unstable. So this is the Z test. Any questions on this? Any questions on this? Okay. So this is very, very simple, but actually when we apply this, right, a little complexity that is going to come. Now actually we wanted to identify whether one body is there on top of the other body. So let us say there is one body. So I will draw the diagram here. Let us say there is one body like this, and then there is one more body which is just touching like this. And let us say the radius of curvature of this particular first body, I call this as second. So this is rho 2, and the radius of curvature for this one is rho 1, let us say. See this, there is one body, so I have just drawn a portion of the body. So there is one body like this, and there is one more body on top of this particular body, and the radius of curvature for this one is rho 2, and the radius of curvature for the top body is rho 1. Then I am asking a simple question, whether the equilibrium, currently actually it is under equilibrium condition, let us say, whether this equilibrium is going to be stable or not. Or actually for what value of theta, or for what values of rho 1 and rho 2. So this is going to be a stable equilibrium or not. So such kind of questions if it arises, right? So there is a specific derivation on that, how we can conclude that. Let us say this is an irregular body, right? So this is having a circular radius at this location, but on top of this, right, it may be regular circular shape or may not be. Let us say this is the position of the center of gravity for this. I call this as G1. So for the top body, the center of gravity is at a height of h from this location. At a height of h from this location. Now the question is whether the top body is going to be under stable equilibrium or not. Right? So to calculate that one, so just note down the problem statement. Based on that, actually, we are going to derive the derivation. This is the theorem. A body rests in equilibrium upon another fixed body. The portions of the two bodies in contact have radii of curvature. The portions of the two bodies in contact have radii of curvature rho 1 and rho 2 respectively. The center of gravity of the first body of the first body is at a height h above the point of contact. Is at a height h above the point of contact. And the common normal makes an angle alpha. Makes an angle alpha with the vertical. Prove that the equilibrium is stable. Prove that the equilibrium is stable or unstable according as h less than or greater than rho 1 rho 2 by rho 1 plus rho 2 cos alpha. So this is the problem statement. See this, there is one body here, on top of that there is one more body whose center of gravity of the top body is at a height of h from the point of contact, and the common normal is this line. So this common normal is making an angle of alpha with the vertical. Now actually this body which is under equilibrium condition, whether it is having a stable equilibrium or not, so depending upon this particular condition where rho 1 rho 2 are nothing but the radius of curvature for the top body and the bottom body. Got it? I hope you understood the problem statement. Now we have to prove this. Done? Noted? Now actually let us prove this. So for this actually we will be using Z test to identify whether the equilibrium is stable or not. So when we are using the Z test, right, first actually you need to express the Z value in terms of theta. So let us say this is the common normal and this is the center of curvature for the second body and this is the center of curvature for the first body. So this is the center of curvature for this body and this is the center of curvature and this is the radius of curvature for this body, and rho 1 is the radius of curvature for the top body. Now let us say I join this line and this length is, let us say the value is k of magnitude k, and if this angle is alpha and this is also a parallel line to the vertical line, then this angle also it will be equal to alpha, right? So this is also alpha. Now I call this angle as beta. Then this angle, right, this angle is going to be pi minus alpha plus beta, because in a triangle all the angle sum is equal to 180 degrees. Now here suppose if this body is slipped to a different location like this, that means this is rotating like this without any slip. Now let us say the new point of contact, this location, right, so is shifted like this, let us say. So this is rotating like this and then actually it is coming to this location. and this is the new common normal now. Got it? So this point actually I call as A1, and this point I call as A2, and this point A1, when it is rotated like this, right? So automatically it will come to a different location like this. I call this location as B. I hope you understood. Just actually this top, let us say this is a sphere, and this sphere actually trying to roll. If it is trying to roll, right, this point of contact will go out to this location, and there will be a new point of contact that is going to come here. Got it? Is this understood? And then correspondingly this one will be rolled to this location, right? So this is O1 becomes O2 now. So that means when it is rotated like this, it will come, and this line whatever is, right, so this line will be this one. I call this as G2. So this G1 is coming out to be G2, and A1 became B and O1 became O2. Let us say it is slipped for a location, so for an angle of theta. This angle is theta. And then what will be this angle? What will be this angle? G2 O2 B. Can somebody tell me what is this angle? Is it alpha or beta? It will be beta, because this triangle is trying to rotate like this. Same triangle actually rotated like this. Then this angle is going to be beta again, and this angle is going to be alpha. Got it? And this arc length, so arc length A1, A2 is equal to BA2. So is this statement true or not? The arc length A1, A2 is equal to BA2. See this, when two different objects like this, suppose these two chalk pieces are there. Now actually these two are rolling on top of the other, right? Then actually whatever the length it is traced by this chalk piece is exactly equal to the length traced by this one as well. That means this curved surface which is on the top, right? So the same rotation that happened, right? So that means the same length whatever it is going to be covered by the bottom surface, the same length is going to be covered by the top surface as well. That means this length and this length, because initially these two are in contact. Now actually see this. So if you take like this, these two are rotating like this. This point of contact, if you notice, so from this length, initially my two fingers are like this in contact. Now actually when it is rotated, this length and this length should be exactly equal, right? So A1, A2 is equal to BA2. And from there actually I can get a relation. Let us say this angle is theta and this angle is phi. I call this angle as phi. Now this angle, so A1, A2 is equal to rho 2 theta, and the same thing is equal to rho 1 phi. Can I write like this? Because actually this is a circle. So on this circle length, this arc length multiplied by, this arc length is nothing but L equal to r theta. R is nothing but the radius of curvature and angle is nothing but phi. So rho 1 phi is equal to, in this case, rho 1, rho 2 is the radius of curvature for this particular arc, and it is making an angle of theta. Then it is equal to rho 2 times of theta. If you take the derivative of it, rho 2 d theta equal to rho 1 d phi. So this is one relation. Or d phi by d theta is equal to rho 2 by rho 1. So this relation actually we are going to make use of it down the line. So that's why actually we have derived this relation. Now actually this is the new center of gravity. I wanted to express this new center of gravity which is at a height of z from the bottom. So this is at a height of z from the bottom. Now this z value I wanted to express as a function of theta. Because actually earlier actually in the previous z test, right, I asked you to express z as a function of theta. Now, this movement is causing certain angular displacement. This angular displacement is causing for a value of z. And for this z, actually, I wanted to identify d square z by d theta square, whether it is going to be positive or not. So, this z value, if I wanted to express as a function of theta, I need to be doing all these things. Got it? Now, so this is the height. So this is G2. I call this as L. So Z is equal to, I call this as M. So Z is equal to ML. So ML is equal to LO2 plus O2M. So O2M is this height. And this height actually I can express as a function of ρ1 plus ρ2, because actually in the problem statement what he has given is only this angle alpha and the radius of curvature values. But we have introduced many other variables like alpha, beta I have introduced, phi I have introduced, theta I have introduced. So all these variables are actually intermittently coming. So down the line we need to be eliminating that. So as and when there is a possibility of using the given constant values, we can make use of that. So this value is again ρ1 and this value is again ρ2. Sorry, this is ρ2 and this is ρ1. Then this entire length OO2 is equal to ρ1 plus ρ2. So ρ1 plus ρ2 is this entire length. So I can express this height as a function of ρ1, ρ2. Now for that actually I need to be calculating this angle. So this is a vertical line. So what will be this angle? What will be this angle? From OO2 to this vertical line. How can we express that angle? Is it 90 minus, what is that? 90 minus F? No. See this. This angle is alpha and this angle is theta. Now, for this vertical line, it is making an angle of alpha plus theta. So this is alpha plus theta. So this is the new position. This is O and this is O2. Right? So when it is alpha plus theta, and if you draw a parallel line like this, then actually as the alternating angles, right? So this is going to be alpha plus theta. So you can express this angle as alpha plus theta. So that is this angle. And then you know this angle alpha and you know this angle as beta. But you wanted to express OL. So you wanted to express LM. So LM with the known values. And this length actually I have called this as K, and this is going to be K after the rotation. Then this height you can express as K times of this angle. I call this angle as some gamma. So gamma can be expressed as and angle OO2M is equal to alpha plus theta. So let gamma be the angle O2G2L. Sorry, gamma be the angle G2O2L. So this is equal to gamma, and this can be expressed as, so 180 minus alpha plus theta plus phi plus beta. This is how you can express it. This is the gamma value, right? So this angle also I found it. Now I can express this value in terms of the known values K, and I can express this value in terms of ρ1, ρ2. So if you write this value, ML is equal to LO2 plus O2M, and this can be expressed as LO2. LO2 is nothing but cos gamma times of K. K cos gamma plus, and this can be expressed as ρ1 plus ρ2 times of cos alpha plus theta. So this is the value of Z I have expressed now. Now actually we have to find out dz by d theta and d square z by d theta square, and then try to identify whether the second derivative is coming out to be positive or not at this location. That is the initial location. So initially the body is at this location and we assume to be, this is under the stable equilibrium condition. Now you have given a little displacement. So after the little displacement, actually so why we have given this little displacement is, you wanted to express the z value in terms of the variable value of theta, so that at what value of theta it is going to be unstable condition. That's what actually you wanted to identify. For that you have given a little displacement so that you can express the z value as function of theta. For that actually we have done all these things. Got it? First you note down this. Now actually we will come back to the derivative of z. I hope you understood this diagram and then these expressions. Any questions on this, you can let me know. So we have got two different relations. So one relation is d phi by d theta is equal to rho 2 by rho 1. And another relation is z can be expressed as rho 1 plus rho 2 times of cos alpha plus theta So these two values actually we have got, which are very, very crucial for us. Now actually, so z is equal to k times of cos gamma is equal to pi minus alpha plus theta plus phi plus beta plus rho 1 plus rho 2 times of cos alpha plus theta. Now further simplification of this. So cos 180 minus theta is minus cos theta. So rho 1 plus rho 2 times of cos alpha plus theta minus k times of cos alpha plus theta plus phi plus beta. Now if you take the derivative of it with respect to z, with respect to theta, dz by d theta equal to rho 1 plus rho 2 times of derivative of cos alpha plus theta. Derivative of cos is minus sine alpha plus theta, and derivative of the inner part, that is alpha plus theta, is going to be 1, and minus k times of derivative of cos is again minus sine. So this is sine alpha plus theta plus phi plus beta. But if you notice, alpha and beta are always constant, and theta and phi are are related to each other based on this relation. So that's why when you take the derivative of it, so k times of sine alpha plus theta plus phi plus beta, and the inner part when you take the derivative of it, then this is going to be 1 plus d phi by d theta. So this is what is going to come extra, because phi and theta are interrelated to each other depending upon this relation. Now actually if you simplify this, dz by d theta equal to rho 1 plus rho 2 by rho 1. So d phi by d theta is rho 2 by rho 1. I have taken the LCM, rho 1 plus rho 2 divided by rho 1. I have taken out. Then actually, so I left with k times of sine alpha plus theta plus phi plus beta minus rho 1 times of sine alpha plus theta. Right? So here actually in the denominator actually there is no rho 1. I have multiplied with rho 1 and then divided with rho 1, and I have taken out in the overall context. So this is going to be rho 1 plus rho 2 by rho 1. Now actually I have taken the derivative of this again, d square z by d theta square. So d square z by d theta square, if you take it, so derivative of k times of derivative of sine is cos alpha plus theta plus phi plus beta, and the derivative of the inner part is 1 plus d phi by d theta minus rho 1 times of derivative of sine is again cos alpha plus theta. So if you further simplify it again, so 1 plus d phi by d theta, this is 1 plus rho 2 by rho 1 again. So this can be simplified as rho 1 plus rho 2 by rho 1 square. So then k times of rho 1 plus rho 2 cos of alpha plus theta plus phi plus beta minus rho 1 square cos alpha plus theta. This is the second derivative. Now actually we have to identify whether this value is going to be positive or not. If it is positive, then we are fine, it is stable equilibrium. If it is negative, it is going to be a unstable equilibrium. Got it? So you note down till this point, we are going to simplify this. Done? So this is important for us now. D square z by d theta square is equal to rho 1 plus rho 2 by rho 1 square multiplied by k times of rho 1 plus rho 2 cos alpha plus theta plus phi plus beta minus rho 1 square cos alpha plus theta. So this is the second derivative. So we wanted to identify the stability of equilibrium at point A1 at this location. So at this location, what are the values of theta and phi at this location? At point A1, because actually we are trying to test the stability of equilibrium at point A1 only. So for that actually to express as a function of theta, we have given the little displacement and tried expressing it. Now initial condition is nothing but at point A1, what is the value of theta? Theta is the angle between these two, the initial position and the moved position. What is the angle? What is the angle? What is the theta value at point A1? So this is going to be 0. And what is the angle for phi? It is again equal to phi. Phi equal to 0, because actually this is overlapped on this. So the angle between this line and this line, if it is 0, obviously the angle between this line and the same line is going to be 0. So phi is also equal to 0. Now if you substitute the values of phi and theta at this location, so d square z by d theta square is equal to rho 1 plus rho 2 by rho 1 square and k times of rho 1 plus rho 2 into, so alpha, so theta and phi you can make it to 0. This value is alpha plus beta minus rho 1 square cos alpha. So this is anyway positive value, as rho 1, rho 2 are the radii of curvature. So hence always positive. So if it is always positive, then actually this part is the deciding factor to have the Z min or Z max. So the equilibrium is stable only if k times of rho 1 plus rho 2 cos alpha plus beta minus rho 1 square cos alpha is greater than 0. So this is the only condition for the stable equilibrium. If it is less than 0, it is unstable equilibrium. So this less than or greater than will decide whether the equilibrium is stable or not. Now actually, here actually we have introduced the new variables beta and k. So we have to eliminate those values with the known values. The known values are, this h is actually given and alpha is given and rho 1, rho 2 are given. So these are the three initial parameters which were given. So alpha you can make use of it, h value you can make use of it, and rho 1 and rho 2 you can make use of it. Rest of the variables you need to be eliminating it. Now actually to eliminate that, what we can do is, if you increase this to this height, let us say I have completed a right angle triangle here. Now here, this length we know that this is going to be rho 1, and this length we know it is going to be k value, and this angle is alpha and this angle is beta, and this exterior angle will be alpha plus beta. Got it or not? Exterior angle is alpha plus beta. Then rho 1 cos alpha is equal to, since rho 1 cos alpha is equal to, rho 1 cos alpha is nothing but this height, because this is a right angle triangle. So this length is rho 1. Rho 1 cos alpha is this height, which is equal to h plus this height. So I call this as Q. So rho 1 cos alpha is equal to A1G plus GQ. So A1G is h plus GQ is k times of the exterior angle cos of alpha plus beta. So this exterior angle is alpha plus beta. So k times of cos alpha plus beta plus h is equal to rho 1 cos alpha. So why we have bringing this one is, this k times of cos alpha plus beta, what we have got is k times of cos alpha plus beta here. So k times of cos alpha plus beta you can replace straight away with rho 1 cos alpha minus h. So this value actually we are going to replace it here. Now from this relation, so if you put it here, then rho 1 plus rho 2 k times of cos alpha plus beta can be replaced as k rho 1 cos alpha minus h minus rho 1 square cos alpha. And this value, if it is greater than 0, then we can say that the equilibrium is under stable condition. Now if you notice, all are known values here. Got it? All are known values. Rho 1, rho 2 is known value, and h is a known value, and alpha is a known value. Got it? So you can note down this. So we will try to analyze this equation physically, what it means for us. So we have got the stability condition as rho 1 plus rho 2 times of rho 1 cos alpha minus h minus rho 1 square cos alpha is greater than 0 is stable. Now if you simplify this, rho 1 square cos alpha minus rho 1 plus rho 2 times of rho 1 cos alpha minus h times of rho 1 plus rho 2 minus rho 1 square cos alpha is greater than 0. So this, if you further simplify it, rho 1 square cos alpha plus rho 1 rho 2 cos alpha minus h times of rho 1 plus rho 2 minus rho 1 square cos alpha greater than 0. So this rho 1 square cos alpha and this rho 1 square cos alpha will go out. Now rho 1 rho 2 cos alpha is greater than h times of rho 1 plus rho 2, or cos alpha by h is greater than 1 by rho 1 plus 1 by rho 2. Got it? So in the problem statement, actually he asked us to prove that rho 1 rho 2 by rho 1 plus rho 2 format. So that is the same thing you can even express as rho 1 rho 2 cos alpha by rho 1 plus rho 2 is greater than h. So this is the condition. Got it? So rho 1 rho 2 cos alpha by rho 1 plus rho 2 is greater than is equal to h, greater than h is the condition for the stability. Suppose if it is less, then actually it is the unstable condition for us. Now here, this is the simplified form of it. Cos alpha by h greater than 1 by rho 1 plus 1 by rho 2. So rho 1 rho 2 are the radius of curvature which are fixed for the particular portion of the body. So this is rho 1 rho 2, and this h is the height of the center of gravity for the top body above the point of contact. So that is the height. And this alpha is the initial angle made by the point of contact or the radius of curvature line or the common normal with respect to the vertical line. Suppose we take one case. Suppose actually there is one semicircle like this. On top of that actually I have kept one ball like this. Now actually I am asking whether this ball is under stable equilibrium or not. For what values of this rho 1 and rho 2? So this is going to be stable equilibrium. Now here actually this is the height of the center of gravity. So the body center or the center of this sphere is nothing but the height of the center of gravity above the point of contact, which is going to be h. Now if I draw a vertical line like this, now this is the common normal and which is the vertical line again. That means here alpha equal to 0. Right? So alpha equal to 0. Now let us say, so the radius of curvature for this one is rho 1 and the radius of curvature for this one is rho 2. Then, so depending upon the size of this particular body, so this top body may be lesser size or more size. Suppose actually if I have actually this kind of semicircle and this kind of ball, that is one case. And another case, I have this kind of semicircle but I have this kind of ball. Now actually in both the cases actually whether the body is under stable equilibrium or not. So for that actually you can identify the values of rho 1 and rho 2 which will decide the stability of the equilibrium here. Now initially, so this angle is making an angle of 0. So this is the vertical line and this is the common normal line. This common normal line is making an angle of 0 angle with the vertical. That means cos alpha equal to 0. Then the simple condition is 1 by h is greater than 1 by rho 1 plus 1 by rho 2. So this is the condition which will decide whether the equilibrium is under stable or not. Got it or not? This is as simple as this. And all the problems what we are going to solve based on this particular formula. Got it? Any questions on this? I hope you understood the derivation. That is very important. So this is nothing complex. Only thing is identification of these angles, bringing the appropriate angles and eliminating the same angles so that you will be arrived at the appropriate location of your answer. For that is a little complicated. But the procedure is straightforward and simple. You need to identify the z value which is nothing but the height from the ground, which is a function of theta. And then you can find out the derivative is anyway 0 as per the principle of virtual work. And the second derivative value is very crucial for us. If it is positive, then actually the stability is going to be, the equilibrium is going to be stable. And if it is negative, then the equilibrium is going to be unstable. So if it is, for that you wanted to identify d square z by d theta square for the appropriate conditions. Here in this case, when it is making an angle of alpha, so this is a more generic case what we have analyzed. So this is the peculiar case wherein one on top of the other. So straight away alpha equal to 0. I have taken that as a variable so that actually I can generalize the equation. That is one case. And another case is like rho 1 and rho 2 are the values actually which will decide the stability of equilibrium. Both plays equal and important roles at the point of contact. And this h value, if you notice, this is the center of gravity. Many people think that actually the center of gravity might be at this location of O1. That can be there, but that is one possible case. But actually depending upon the shape of this particular top body, the center of gravity may be this side or maybe that side. Or actually biased body, if you take it, let us take biased sphere. Biased sphere, we mean the shape is spherical only, but actually one side density of the ball is more. Then the center of gravity is going to be shifted towards the point where the density is more. Got it? So that is the kind of scenario what we have analyzed in this particular case. Got it? So otherwise actually if the center of gravity is here itself, then definitely it is going to fall down. And fundamental rule is this line is always vertical. Why? Because unless if it is not vertical, then the body is anyway going to be under, so the body is anyway undergoing to be the unstable condition, because the center of gravity has to be on top of the point of contact. Otherwise, if it is tilted a little bit, automatically it will fall down. It won't stay there itself. That means the body is not under equilibrium itself. Then actually there is no point in questioning whether the equilibrium is stable or not. Got it? So that's why This is uneven body, what we are analyzing. The shape may be spherical, but the density may be distributed to one side. So this is uneven case. This uneven case is a more general case. That's why we have taken general case of making an angle of alpha and uneven distribution of the mass, so that the center of gravity is exactly on top of the point of contact. The same condition is even satisfied here also. The center of gravity is exactly at the middle, or this is an even sphere. So that is, the center of gravity is exactly middle. And if you notice, from the point of contact to this particular point, this is exactly on top. That means on the same straight line, exactly. So the point of contact and the center of gravity of the top body has to be on the same vertical line. This is the rule, and this will be the rule. Why? Because even if it shifts a little bit, then automatically it goes out of equilibrium case. Then actually there is no point to calculate the stability of equilibrium. I hope you got it. Got it? Okay, great. So this is the derivation I am talking about. So in the next class actually I will be taking only one class. So that class actually I am going to solve some of the problems based on this understanding. With that actually we are done with this statics part. So if you notice in the entire chapter of statics, right, if you notice only one aspect we are always talking about, that is the equilibrium of forces. So that actually I hope you noted down this. Noted? Okay. Right, so in the entire statics, right, so we are dealing with only one aspect, that is the equilibrium of forces. So rather than calling this as a static, actually you can call this as equilibrium of forces. But in this case actually we have divided this into equilibrium of forces for coplanar forces. And the next one actually we dealt with 3D forces. And then actually we used the principle of virtual work. To calculate unknown force. When the body is under equilibrium. So this is what we have done. And then actually we tried analyzing the stability of equilibrium. So these are the things actually what we have dealt. Now, before this equilibrium of body, right, so there are certain fundamentals that we have to be aware of it. Those fundamentals are, one is, so movement of the force. So movement of the force actually we have to be aware, and linear equilibrium and rotatory equilibrium. So these aspects actually we have to be aware of it. And before even the movement of the force, right, you have to be aware of what is a force and the properties of the force. So three important properties of the force, that is the point of application of the force and line of action of the force and the magnitude of the force. So these are the three important properties. So based on these properties actually we arrived at movement, and then these movements and the force together will decide the body is under equilibrium or not. Those conditions actually we have analyzed in detail. Now to understand all these things actually we learned something called vectors. That is, so vectors are the fundamentals for the entire topic like this. So this is what is the complete statics what we have analyzed. But if you notice, there is only one topic we are dealing with, that is the equilibrium of forces, and all these things are the necessary requirement to understand this equilibrium of body. So all these things actually we dealt in detail, and then this equilibrium of forces actually different ways, that is coplanar forces and non-coplanar forces. And then in case of unknown force of an equilibrium system, we use the principle of Virchow-Wahlberg to identify the unknown force, and then we have analyzed the stability of equilibrium. That's all. Right? Yeah. Common catenary also is a part of this equilibrium of forces again. Yeah. So this is what is the complete statics syllabus. I hope you got a fair clarity on this particular topic. This is not tough at all. Only thing is you have to be aware of all these aspects, nothing more than that. And that too, this is a small topic. You don't need to deal with many of the things, and not many models also there. Got it? Yeah. So anything? Okay. So that's all for today. In the next class, I'm going to solve some of the problems based on this understanding. With that, we will close this topic. Yeah. So we'll be starting with the dynamics part of it. So till then, good night. Thank you.